The ground is shaking beneath your feet, not in one city, across every continent. 1,500 volcanoes erupting simultaneously, ash columns punching 30 kilometers into the stratosphere, airplanes vanishing from radar screens worldwide. Within hours, daylight fades to darkness and temperatures begin to fall across the globe. What would actually happen if every volcano on Earth erupted at the same time? The answer starts not with fire raining from the sky, but with what happens in the first 10 minutes on the ground. Inside the magma chambers of 1,500 active volcanoes, dissolved gases like water, carbon dioxide, and sulfur dioxide rapidly expand as pressure drops. This rapid decompression forces magma fragmentation, shattering liquid rock into a pressurized, supersonic mixture of gas and ash. While gentler effusive volcanoes, like those in Hawaii, release slow-moving lava flows, explosive subduction zone systems, like the Cascade Range or the Andes, rupture violently under immense gas overpressure, launching massive columns into the sky. The primary local killer in these explosive events is not flowing lava, but pyroclastic density currents. These superheated, ground-hugging avalanches of toxic gas, ash, and pumice race down the volcanic slopes at speeds between 200 and 700 kilometers per hour. Reaching temperatures of 300 to 800 degrees Celsius, they instantly incinerate and bury everything in their path, leaving no time for evacuation. In 1902, Mount Pelée demonstrated this terrifying speed when a pyroclastic current engulfed the coastal town of Saint-Pierre in under 2 minutes, erasing the community and killing 30,000 people. Only a few survived near the impact zone. Among them was Lugger Silbaris, saved because the thick, windowless stone walls of his prison cell shielded him from the extreme heat and suffocating debris. As the ash plumes rise, intense friction between colliding particles creates electrostatic charges, generating brilliant displays of volcanic lightning directly above the vents. Simultaneously, the extreme heat melts glaciers and snowcaps, mixing water with loose ash to trigger lahars, dense, fast-moving mud flows that bury entire valleys. These immediate hazards threaten the major volcanic belts of the world, particularly the Pacific Ring of Fire, where hundreds of active vents lie close to exposed human settlements. The seismic waves from these concurrent eruptions ripple through the Earth's crust, collapsing buildings, fracturing roads, and severing local lifelines before the ash even settles. For communities living within the shadow of these active tectonic belts, the first 10 minutes are a desperate fight for survival against a local disaster that is already expanding into a global atmospheric crisis. Within 60 minutes, local kinetic destruction transforms into an atmospheric chokehold. Superheated gas and ash mixtures blast through the troposphere, passing the cruise altitude of commercial flights. In 1991, Mount Pinatubo's column reached 35 kilometers. In 2022, the submarine eruption of Hunga Tonga Hunga Ha'apai shattered that record, launching a plume 58 kilometers high into the mesosphere. With 1,500 active volcanoes erupting simultaneously, thousands of these columns punch through the tropopause, merging into an expanding ceiling of glass and stone. As the plumes rise, the heavier silicate ash begins to separate from the lighter sulfur dioxide gas. While the sulfur continues its upward journey to alter the climate, the ash remains a direct threat to global aviation. This is not soft dust. Volcanic ash consists of jagged shards of rock and silica with a melting point of over 1,000 degrees Celsius. Inside a jet engine, these particles melt instantly, coating turbine blades in liquid glass and choking the airflow. In 1982, British Airways Flight 009 flew into an invisible ash cloud over Indonesia, losing all 4 engines within minutes. 7 years later, KLM Flight 867 suffered the same total power loss over Alaska. Both flights barely restarted their engines after diving thousands of meters through the dark. Under international civil aviation protocols, flights must ground when ash concentrations exceed 2 milligrams per cubic meter. But as thousands of plumes spread, tracking systems fail. Geostationary satellites and ground-based monitoring networks are overwhelmed by the sheer volume of data, forcing an immediate, worldwide grounding of all air traffic. On the ground, massive fires ignited by lava and volcanic lightning release thick soot, mixing with the falling ash to choke out the sun. This first hour does not bring instant human extinction, but it strips the planet of its modern connectivity. Within 60 minutes, humanity is blinded, grounded, and unable to predict the path of the expanding disaster. The darkness descending on the first day brings a heavy, falling rain of pulverized rock. The heaviest, coarse particles of tephra drop out of the sky first, blanketing close-range communities within hours. But the lasting danger lies in the fine silica dust. Measuring under 2 micrometers, these microscopic, glass-like shards remain suspended in the lower atmosphere, transforming the simple act of breathing into a toxic respiratory hazard. As this fine dust settles, it infiltrates critical infrastructure. It coats electrical insulators, causing massive short circuits across regional power grids, while turning drinking water reservoirs into acidic, muddy silt. On the ground, the accumulation rapidly becomes structural. Volcanic ash is incredibly dense. Just 10 centimeters of wet ash places over 100 kilograms of pressure on every square meter of a roof, causing homes and industrial buildings to buckle and collapse under the weight. Along the coastlines, the threat shifts from the air to the ocean. When submarine volcanic calderas collapse, they displace massive volumes of seawater. In 1883, the collapse of Krakatoa generated tsunamis between 30 and 42 meters high. These massive walls of water slammed into nearby shores within 3 minutes of the eruption, leaving no time for evacuation and claiming more than 36,000 lives. By the end of the first 24 hours, there is no single, organized global map of the disaster. Instead, the planet is fractured into thousands of isolated, simultaneous emergencies, with each community cut off, blind, and fighting its own distinct battle against falling stone, rising water, and suffocating air. By the 4th day of the crisis, local kinetic destruction shifts into a systemic breakdown of global infrastructure. The atmospheric threat of falling dust rapidly becomes a direct assault on the electrical grid. Rain and atmospheric moisture mix with the suspended silicate, turning dry insulators into a highly conductive paste. During the 1992 Mount Spur eruption in Alaska, wet ash coated powerline insulators across Anchorage, causing massive short circuits and forcing utilities to shut down major sectors of the grid. Now, this phenomenon repeats on a global scale. Power plants and regional transmission networks fail in rapid succession as heavy, conductive mud short-circuits transformers on every continent. As the lights go out, global communications degrade. Microscopic silica shards suspended in the stratosphere scatter high-frequency radio waves and degrade satellite signals, causing GPS networks to lose lock and positioning systems to drift. On the ground, emergency radios fail as fine dust clogs the air filters of transmission towers, overheating the circuitry. This loss of signal immediately halts maritime transport. Cargo vessels, already navigating without air support, slow to a crawl or anchor outside harbors as GPS navigation and port radar systems fail. These delays convert localized physical damage into global supply chain paralysis, trapping critical resources in transit. Simultaneously, a planetary sunshade begins to alter the biosphere. Massive injections of sulfur dioxide oxidize into reflective sulfuric acid aerosols, causing a sudden drop in direct sunlight. In the major agricultural regions of the North American plains and Europe, the loss of photosynthetically active radiation disrupts planting cycles. Temperatures slide downward, stalling crop development. Emergency response systems, designed with the assumption that unaffected regions can rescue those in crisis, collapse. There are no unaffected regions left. Inside the stratosphere, far above the reach of weather and rain, the immense payload of injected sulfur dioxide gas begins a silent chemical transformation. Over days and weeks, this gas reacts with water vapor and sunlight, oxidizing into highly reflective droplets of sulfuric acid. This stratospheric aerosol layer is the true engine of a volcanic winter. While heavy, jagged silicate ash is dense and settles back to Earth within weeks, these microscopic sulfate droplets are light enough to loiter in the upper atmosphere for years, driving long-term radiative forcing. The resulting planetary cooling does not come from the volcanic heat or the lava itself, but from the physical block of sunlight. These glassy aerosols act as billions of microscopic mirrors, scattering incoming solar radiation back into space. Historical events illustrate this scale. In 1991, Mount Pinatubo's injection of 20 million tons of sulfur dioxide lowered global temperatures by about half a degree Celsius. In 1815, Mount Tambora released far more, causing a worldwide temperature drop of nearly 1 degree. Scaling this to 1,500 simultaneous eruptions pushes the planet into uncharted territory. Climate models simulating this level of atmospheric loading do not point to a single certainty, but rather a range of potential outcomes. Depending on wind currents and particle accumulation, these models estimate a global surface temperature drop of between 2 and 5 degrees Celsius within months. As this aerosol veil wraps around the Earth, secondary chemical reactions begin. The surfaces of the sulfate droplets facilitate the destruction of stratospheric ozone, thinning the planet's radiation shield and allowing harmful ultraviolet rays to reach the surface. The isolated local disasters of the first week have now merged into a single, coordinated global climate event. 12 months into the global volcanic winter, the initial weather anomalies harden into a systemic collapse of food production. In temperate zones, the primary growing seasons have ceased to exist. Freezing temperatures and a 15% reduction in solar radiation halt the photosynthesis of staple crops, wiping out wheat harvests across the North American plains and devastating European agriculture. With global grain reserves, which typically cover only 90 days of consumption, completely exhausted, food is no longer a commodity, it is a tightly rationed sovereign asset. This pressure extends deep into the oceans. Sulfuric acid deposition and prolonged darkness disrupt the photic zone, halting marine productivity at its source. Without sunlight, phytoplankton populations collapse, triggering a rapid decline in global fisheries and cutting off the primary protein source for 3 billion people. Inside local communities, the crisis moves from empty kitchen tables directly to overwhelmed clinics. The persistent suspension of ultrafine silica dust, measuring under 2 micrometers, bypasses human respiratory defense systems to lodge deep in the lungs. Obstructive pulmonary disease rates soar, while acidic ash runoff continuously breaches municipal water systems, neutralizing chemical treatment plants and contaminating open reservoirs with toxic levels of fluorine and selenium. As municipal infrastructure fails and regional food supplies evaporate, human geography begins to fracture. Borders buckle under the pressure of millions fleeing the freezing, darkened northern latitudes toward equatorial regions. This mass migration is a chaotic, desperate flight from resource starvation, transforming a planetary geological event into an existential test of human resilience. Against a disaster of this scale, the question of human survival is not a matter of speculation, but of geography and system design. Humanity would not go extinct. Our sheer numbers, geographic distribution, and technological adaptation ensure that pockets of population endure. The areas most likely to weather the volcanic winter are those insulated from surface disruption, regions utilizing geothermal power, subterranean infrastructure, and massive strategic food reserves. Iceland, with its extensive geothermal grid and decentralized agrarian communities with localized power generation, become the primary strongholds of the post-eruption world. Secure underground facilities like the Svalbard Global Seed Vault, carved directly into the Arctic permafrost, protect the genetic blueprints of global agriculture. While a massive accumulation of ash might block physical access to the vault for years, its reserves, alongside regional germplasm repositories, remain the foundation of long-term recovery. Once the skies begin to clear, these stockpiles will provide the genetic material to restart cultivation in an altered environment. A common assumption is that our sophisticated monitoring network would prevent such a catastrophe. It would not. The United States Geological Survey and the Smithsonian Institution monitor approximately 1,500 active volcanoes daily, but these networks are built to manage isolated regional crises. In a synchronized planetary event, the sheer volume of seismic, acoustic, and satellite data would instantly saturate communication pipelines, creating an overwhelming analytical burden. Knowing an eruption is occurring does not equal safety. When the systems of evacuation, food distribution, and power maintenance fail simultaneously across every continent. Early warning is useless when there is no safe haven left to run to. The timeline for recovery is measured in 2 distinct phases: geological and societal. Climate models show that stratospheric sulfate aerosols gradually sediment out of the atmosphere, allowing global temperatures to stabilize within 5 to 10 years. But the repair of human society operates on a much slower clock. The physical destruction of the electrical grid, the complete collapse of global transport, and the loss of generations of technical knowledge mean that while the sky may clear in a decade, the process of social repair will extend far beyond the return of climate stability. Rebuilding a globalized civilization will take centuries. We treat the solid ground beneath us as a permanent guarantee, but geology warns it is merely a temporary truce. Our entire civilization exists by the grace of a restless planet's quiet intermission. The ultimate question isn't when the Earth will wake, but whether we'll be ready when it does. Share your thoughts on our survival chances in the comments below.